So what about multiplying? Here we have two rational expressions. We're asked to multiply and then to simplify the results as much as possible. Let's move over to the multiplying fractions question, just for some motivation. So if I want to multiply 18/25 by 5/6, what are my options? What can I do?
Reduce.
So I can reduce. Yeah, that's certainly a possibility. Let me actually copy-paste this, because I want to do it in two different ways. So what would reducing look like if I chose that for my strategy?
3/5 and 1/2, or 1/, just 1.
Yeah, right. So what you're seeing there is you're looking across both of the fractions that are here and already looking for common factors. Right? The 18 and the 6 have what factor in common?
6.
6. And so if you divide 18 by 6, you get 3. And if you divide the 6 by 6, because we have to do the same thing on top as we do on the bottom, ended up with 1. And the 5 and the 25?
5 and 1.
5 and 1. And there you got that by dividing by
Greatest common factor.
their common factor, which is 5. So 5 divided by 5, and 25 divided by 5. 5. And so, in the end, what survives? On top, a 3 and a 1, and on bottom, a 5 and a 1. So how does this reduce? What's the fraction?
3/5.
3/5. So reducing across the multiplication sign is one strategy that we can use. And then we could use it for this rational expression product over here as well. Before we implement that, let me ask, what's the other strategy? If you're not reducing right away, how do you multiply two fractions?
Multiply across.
Multiply straight across, right. So in that strategy, we would just go straight across with the 18 and the 5. 18 times 5 is 90. Straight across with the 25 and the 6. 25 times 6 is 150. And then we would be tasked with reducing that fraction.
So the top answer on thing would be 4x plus 24.
See, the problem, it's not really a problem, but the challenge of multiplying first is that now your reduction step is a little bit harder. Right? Because between 90 and 150, your greatest common factor is bigger. You have to go all the way up to 30 to find the greatest common factor. Divide by 30, divide by 30. But sure enough, when you do that, you get the same 3/5.
You can take off the 0 too, right? You get 9/15.
That's also true. Yeah, we could have just divided by 10 first to knock off the zeros, and then saw it as 9/15. But yeah, whichever process you prefer. Okay, so those same options are available to us for this rational expression. We could, on the one hand, just decide that we want to multiply straight across x plus 2 times 4x plus 12, and then also x squared plus x plus minus 6 times x plus 3, and just multiply them across. The problem is that the temptation, I am going to recommend doing this, but the temptation when we do that is going to be, oh, we should FOIL, right? I'm just going to try to whip through the FOIL here real quick. 4x squared plus 8 and 12 is 20x plus 24. And then downstairs, you would FOIL this gigantic thing out and get something like x cubed minus 3 plus 1, negative 2x squared, negative 3 minus 6 minus 9x plus 18. This is a very tempting thing to do, even though it looks nasty. People's knee-jerk reaction is, I'm multiplying these polynomials, I should FOIL them out and do it in their gory detail. And that's fine. This is a correct expression for the product, but that's not simplified, probably. And if we wanted to simplify this, what would we have to do? First step that we would have to do if we were trying to simplify? To factor. Yeah, we'd have to factor. We'd have to go GCF. We'd have to look for factors in the trinomial form. We'd have to look for special products. We'd have to look for factors by grouping. We would have to refactor. So in other words, foiling is a step backwards, because we're just going to have to unfoil it again anyway when we want to simplify it. So this is an important matter of strategy. Don't FOIL until the absolute last possible instant in a problem. Don't distribute. So we waited in example number 1 to do any distributing until we were sure that we had crossed out all the common factors that we could cross out. Leave everything factored as long as absolutely possible. So don't foil. Resist the urge to foil until the very last second in a problem. So from there, here's my first recommendation. We're going to multiply across. And the way I like to do that, especially since these fractions are written together so closely, I'm just going to take those two fraction bars and make them 1. Whatever. But in doing so, I want to be careful that the old numerators are still grouped with parentheses and that the old denominators are still grouped with parentheses. So I've taken this two fractions and I've made it into one big fraction. Okay, see what I'm doing? I'm multiplying the two old numerators. I'm multiplying the two old denominators. And just kind of saving some space on the page by leaving it in the same place that it started. Okay, so again, here is an expression which is correct for the product, but it may not be completely simplified. So we need to just bring ourselves back to the simplify step. What would you like to do from here? How do we simplify this new rational expression? Robert?
For 4x plus 12, just find the greatest common factor, so it would be 4.
Okay. So we're going to factor 4x plus 12. That allows me to take out a 4. And when you take out the 4, what's left over? X plus 3. So 4 times x plus 12 became, 4x plus 12 became 4 times the quantity x plus 3. I still have that x plus 2 sitting out here as the first factor. What happens downstairs? X minus 3, it looks like I can't do anything with. But what about this thing?
X on the outside of the parentheses.
X on the outside like this? And then what's left over on the inside if I do that?
Plus x.
X plus.
Minus 6.
So there'd be a 1 left over from here. Problem is that this minus 6 right here doesn't have an x in it to begin with. So I can't actually take an x out of all 3 of the terms that are inside those parentheses. The x squared and the x have an x that they can donate, but the minus 6 doesn't. So we can probably still factor this, but we can't do it by considering x to be the greatest common factor.
You find two numbers that multiply into -6 and add up to regular x.
All right, add up to, well, two numbers are not going to add up to regular x, but the numbers have to add up to 1. There we go. So yeah, so we play the sum and product game again in whatever accounting fashion you prefer to sketch it. I like this little diagram. So we're looking for two numbers which multiply together to give you -6 and which add together to give you how much? 1. What pair of numbers fits that description? So 2 and 3, and which of them is negative and which one is positive?
-2.
There we go. -2 and 3 fit that bill. So how does that suggest that we can factor this? How does this green expression over here factor, therefore?
-2, it's x minus -2, x plus 3.
Yeah. X minus 2, x plus 3. Again, the reason for that is when you play the sum and product game, what you're doing is you're finding out how to split that middle term. We know x squared is going to come from x times x. And we can predict that the -6 is going to come from -2 and 3. But if we make that prediction, that means that our other middle terms are 3x and -2x. And sure enough, when we add together all 4 of these terms in the boxes, we get x squared plus 3 minus 2, which is 1, x minus 6. Remember, you can always check your factor problems. Anytime you factor, if you're concerned about whether it's correct, just FOIL it back out, and you should just take a step backwards to where you were. Okay, I said that you'd spend the majority of your energy in these problems just factoring, and we just did. We factored everything in sight. So what happens now?
Do you cancel out like terms?
Cancel out like, I wouldn't call them terms, I would call them factors, but yes, cancel out any factor which is common to the numerator and the denominator. What factor can you see here that's common to the numerator and denominator? X plus 3. It's the only one. And once we cancel the x plus 3s,
So the 4 remains.
yeah, the 4 sticks, because there's no 4 downstairs to cancel it. Likewise with the x minus 3 downstairs, it stays because there's no x minus 3 upstairs to cancel.
And that's done.
And then that's pretty much done. It just depends on how much additional re-simplifying you want to do. So as I mentioned before, resist the urge to FOIL and to distribute until the last possible moment. This would be that moment. If you want, you can redistribute this stuff back out and get a version of the final answer that doesn't have any parentheses. If I write that up here, on the one hand, upstairs we'd have 4x plus 8. And on the other hand, downstairs, x minus 2 times x minus 3, we would have to legitimately FOIL to get x squared minus 2x minus 3x plus negative 2 times negative 3. And let me just extend that fraction bar appropriately here. So that's a last step that you can do. It's a little bit optional, I think. But the important part of these problems is the factoring followed by the canceling. Right?
So you don't even really multiply overall, or just, well, kind of.
My personal taste is not to, right? And in fact, if you do it too early, you're shooting yourself in the foot. Because chances are, if you multiply too early, you're just going to have to refactor later on down the line to find out what cancels. So maybe the rule of thumb is don't multiply until after you're sure you've canceled everything that you can cancel. And you can't be sure of that unless you first factor everything.
And then that last part is optional.
The last part I see as optional. And I think Alex is pretty liberal about letting you leave it in either of those forms as your final answer. Now, if you're on a multiple choice test and this isn't one of the multiple choice options, but this is, then you probably will want to multiply everything back out. But if it's an open response question and I'm the one grading it, I don't mind if you prefer to leave it in the factored form.